Alright, let's get started with weeks 8 and 9 of Engineering 120. During this part of our work together, we'll be exploring the RCX output and how that microcontroller operates. We'll also be exploring how it delivers power to the output and take some current and voltage measurements along with that. We'll also add to that relays and how they operate and how we'll use them to control other devices. Let's look back at our overall system. As we've discussed, we are exploring the elements of a fish tank system that controls temperature and salinity. You may have noticed the instructor model in the classroom on the cart. Up to this point, we've practiced some drawing skills, completed efficiency and flow rate tests on pumps. Additionally, we've worked with LEGO RCX microcontrollers to learn some programming strategies. Now we'll move into the electrical circuits, specifically cascaded switching and power needs. We'll be working on concepts in electricity, and then later, of course, we'll be working on water heating and cooling and the temperature sensor associated with that, mass balancing and for the salt content and the sensor associated with that, and then finally we'll put the system together and work on control. The concepts of frequency, period, and duty cycle cut across engineering disciplines. We'll see how they are applied to voltage control of motor speed, and more specifically, how this changes the power delivered by the RCX to its outputs. Other applications of these concepts occur in signals associated with communication, load and fatigue characteristics and structures, welding process control, and many others. In electrical terms, a square wave is generated by opening and closing a switch. This concept is an underlying principle in communications and computer processing. The sample signal shown here essentially shows a switch on a flashlight being opened and closed. 3 quick pulses followed by 3 longer pulses and followed again by 3 quick pulses. These dot and dash symbols below this happen to be the representative sign for distress, or the classic SOS signal. The corresponding square wave pattern could represent a signal sent to an emergency light. The period of the sample shown here is 40 milliseconds. This pulse again rises and drops, that's the period, and so in 40 milliseconds that's the time for one cycle. As the reciprocal of the period represents how many cycles occur in a second, the frequency of this signal, how often the number of cycles that pass per unit time, is found by inverting the period. And so this particular signal is a 25 Hertz or cycles per second signal. The duty cycle quantifies the shape of the waveform, the ratio of the up portion to the total period. The sample shown here has duty cycles that vary from 25% down on the left-hand side to 50% in the middle, and then finally a 75% duty cycle on the end. Again, the pulse is up for 25% of the time and down for 3/4 of the time on the left-hand side. In the middle, it's up half the time and down half the time, and then finally up 3/4 of the time and down 1/4 of the time here. Let's take a look at a web-based circuit simulator that's fairly simple to use and is intended to demonstrate many electrical concepts. The configuration shown here has a square wave with adjustable characteristics, a switch that's included, and along with, in this space, there's a voltmeter. Okay, what we're focusing on is taking a look at the cycle time, the period, the frequency, which is the reciprocal of the period, and again the duty cycle, which is the pulse width divided by the period. The first example here is a 9-volt pulse with a frequency of 25 Hertz and a duty cycle of about 50%. So let's let this run so you can see that's working. So this is the pulse that's coming out of this voltage generator. If we open the switch, of course it's going to stop operating, and we close the switch and it begins again, watching the waveform down below. This is demonstrating a 50% duty cycle on a 25 Hertz frequency. Let's pause this and take a look at modifying the frequency the duty cycle of this one. So I'll right click on this, use the edit function, and rather than 50% duty cycle, let's go with a very short duty cycle of 10%. And now if we run this again, you can clearly see the 10% up and 90% down on this. Again, the pulse height is 9 volts and it's off for the remainder of the time. So on 10%, off 90%. So let's take another look here. Let's do a right click here, edit this, switch to 90%. Look at the other end of the spectrum and start the model, and you can see that again 90% up and 10% down. So you should become familiar with the formulas for duty cycle and period. Here we'll be using these in class to characterize the output of the RCX. Let's discuss the relationship between duty cycle and averages. The meters that we use in class, like the ones shown here in red, take averages when they're taking measurements. And so if they're receiving a pulse, like the one shown here, where it's got a 6-volt peak over 1/3 of the period, and then for the other 2/3 of the period it's off, it's receiving this 33% duty cycle. The average can be estimated graphically, shown here, but also mathematically. In this case, graphically, it's 6 volts tall and 3 divisions wide, so that's approximately 18. The area is 18. So if you stretch that across the whole period, and in this case the period is 9, that would mean that the height would have to be 2. So this would receive a 2-volt signal. That's what would be displayed on the meter. Now, you can do that mathematically, of course. In this case, the area would be 6 times t over 3. And of course, you reduce that, so it's 2t is the whole total area. So the average height if you stretch it over the entire period, would be 2t over t. And of course, the t's cancel, and you would get 2 volts. So both graphically and mathematically, the meters that we use take averages of the signals that they're receiving. This is a key idea. This is the same signal that the motors receive from the RCX when we modify their speed. And so understanding these characteristics will help us understand how the RCX varies the output voltage and the power delivered to the motors. Okay, we're coming back to the simple circuit that was described during our motor and pump activities. The simple circuit is going to consist of a DC power supply, a switch to control the current flow, and a load or resistor in the circuit. And so this again completes a simple circuit. In this circuit, the power supply provides the voltage that will cause current to flow when the switch is closed. As the current flows through the resistor consumes some energy, and the rate at which it consumes energy is the power absorbed by the resistor. So let's return to the web application and take a look at a situation similar to what the measurements that we'll be taking in class. Before we do that though, just a reminder, we're talking about Ohm's law, and it defines the relationship between voltage, current, and resistance. So for any electrical device, like the resistor shown here, it's the voltage across that resistor is going to be equal to the current passing through it times the resistance of that device. So the common phrase is V equals IR. And the power being consumed by that resistor is going to be the product of voltage and current. So the power is voltage times current. And again, just to reiterate, the units, voltage is measured in volts, current in amperes, and resistance in ohms. And power is in watts, or the units underlying that are in joules per second. Alright, so here a 9-volt power supply is connected to a 100-ohm resistor. Mathematically, this combination should allow about 90 milliamps to flow. And so using the I equals V over R, we can use the 9 volts and the resistance of 100 ohms. So this should be 90 milliamps. If we engage the resistor, or let the activation start, engage the resistor, the switch, excuse me, and hover over the resistor, we can see that down in the lower right hand corner it shows 90 milliamps of current, the voltage drop across the resistor of 9 volts, the resistance of 100 ohms, and the power being absorbed at 810 milliwatts. So if we hover over the wire, it shows the current passing through it, and wires don't drop any voltage. And so you can see that the current is the same throughout each of the devices as I change the hover point. Here the voltage source is 9 volts, and the current delivered by it is 90 milliamps. The switch, of course, has it shows as closed, no voltage drop, and 90 milliamps. Let's change the voltage on the battery to half what it's supposed to be, or 4.5 volts, and see if we get the changes in current that we expect. So if we switch to 4.5 volts, the voltage will drop by half, and so our current should drop in half. So we'd expect about 45 milliamps. So let's operate this one. So now as we hover over the resistor, the voltage applied to it is 4.5 volts, and in the lower right hand part of this image you can see 45 milliamps flowing through it. Now the power has dropped by a factor of 4. Because the power is a product of voltage and current, there happens to be a square function in there that's not obvious, but the power formula can be shown as I squared, the current squared, times the resistance. And so that's why it drops by a factor of 4. Let's change the resistance value to half what it is. Let's stop this model, edit, switch the resistance value, oops, wrong spot, switch the resistance value to 50 ohms. And run this again. Let's stop this. Now as we hover over the resistor, it's returned to 90 milliamps because we've cut the resistance in half and the voltage is in half, so the current's still the same, but the power is much different. Because the resistance value changed, the power is only 450 milliwatts compared to the original 800, and the second one that we did was around 200 milliwatts. So mathematically it works out, so understanding these formulas and how to solve them will be important when you're addressing your problems in class. Stop this. The voltage divider is an extension of the simple circuit. Two resistors, R1 and R2, are connected in series with the voltage source and the switch. The key ideas in series circuits like this are that the voltages around the loop add up to 0. That said, the voltage source adds voltage, and the voltage drop across each of the resistors subtracts voltage. The total resistance in the circuit is the sum of R1 and R2. In this case, 100 ohms plus 100 ohms is 200. Finally, the current is the same. Once the current starts flowing, it's going to be the same throughout the whole circuit. And it follows Ohm's law. So the current flowing through the circuit is the voltage divided by the sum of the resistance. And so the current is voltage divided by R1 plus R2. Let's take a look at this situation with two identical resistors. Alright, this model is a 9-volt power supply and 200 ohm resistors again. The total resistance is the sum of these two, so we have 200 ohms of resistance, a 9-volt power supply. We should expect to see about 45 milliamps passing through this as a result. So let's start this working. You can see on the bottom of the screen, down on the left-hand side, we've got the power supply displaying its values, 0 current and 9 volts because the switch is open, and no voltage on either of the resistors. And so as I close the switch, you'll see current start to flow in the model, and as we hover over resistor 1, you'll see it is in the lower right, it has 45 milliamps and 4.5 volts voltage drop. And as I hover over the second resistor, it also has 45 milliamps and 4.5 voltage drop. Now that's true because these two resistors are identical. Alright, so let's modify the resistance of R1. We'll open the switch, edit R1 to 50 ohms, and now we'll see the effect of this on the system. So switch is closed, and the current has changed. The current going through the system is 60 milliamps now. When you hover, you can see that by hovering over the power supply here, 9 volts, 60 milliamps. Similarly, the current drop through each of the resistors is now changed. So the voltage drop in resistor 2 here is current times resistance. So at 100 ohms, 60 milliamps, it's going to have a 6 volt drop. And as we come down to R1, 60 milliamps, 50 ohms is a 3 volt drop. And so again, reinforcing that as a voltage divider, the voltage from the power source is divided between the two resistors. So just for clarification, again, the voltage drop on the bottom is 3 volts and the voltage drop on the top is 6 volts. So let's open the switch for a second. Let's edit this one. We'll modify it to 50 ohms, and then return the resistor R1 to 100 ohms. Activate the switch and take a quick look at this. So now the voltage drop across the 50 ohm resistor on R2 now is 3 volts, while the other resistor is now 6 volts. So they have reversed, and this demonstrates a little bit of how a voltage divider can be used to modify 9 volts to either a 6 volt power supply or a 3 volt power supply. Okay, let's take a look at relay operation and the idea of cascaded switching. Relays are generally used to trigger actions between systems. For comparison, when a household light switch is closed, the energy or current needed to power the lamp passes directly through the switch. In contrast, the garage door opener button usually energizes a small relay that powers the motor that opens and closes the garage door. This is an example of cascaded switching. It allows a small amount of energy to be used to control another energy source that can power a larger load. So the garage door opener takes much more energy to open, and the small switch on the wall in the garage would typically allow it to operate. So that's a basic relay function. We'll be dealing with that same concept here. So each relay has a coil, and this sketch here is also duplicated in your reading material. It has a small wound coil with an iron core, and so this creates an electromagnet. In order for it to actually have enough magnetic strength to pull the switch closed here between C and D, it has to have a certain amount of voltage applied to it. This happens to be a normally open set of contacts, and so when it is activated, the switch closes. You can have switches that are closed, and then when it's activated, it will become open. So once again, the key concepts here is there's a certain coil voltage that relays need, and they're designed to operate with. The contacts will be normally open or normally closed, and the applied voltage energizes the small electromagnet to close the contacts. If the contacts are connected to another circuit, then that circuit is turned on, like the garage door opener example that we discussed. So applying the correct voltage ensures correct operation. This is where the voltage divider comes into play. So here's another example of how the circuit simulator can help us understand a little bit about how the relays work. So the highlighted portion right here, the relay, has a resistance included in it. That's the coil resistance. It's about 125 ohms, and if we describe it as R1, it makes sense for part of the voltage divider circuit. We can use what we know about the coil resistance, that 125 ohms, and the desired coil voltage to determine what value of R2 is needed. In this case, 100 ohms should work. If we do the math here, we know we have 9 volts. The relay needs 5 volts applied to it, and so we can use this equation here to establish what R1 and R2 should be. And so I'm going to right click on this, edit this, put in 100 ohms. Okay, your experience in class will probably be a little bit different, but let's take a look and see how this operates. As we close the circuit and I allow the circuit to operate, The voltage supplies coil through the relay. That relay gets magnetized and pulls the switch closed. So I'm going to open and close this a couple of times. When the switch is open, no current's flowing, and the switch remains open. These are the contacts switching back and forth. Let's operate this one more time. So we can see here, this is the cascaded switching piece as well. So this switch activates the relay portion of the circuit, right? And when the relay closes, it closes the contacts on the second circuit. So a higher voltage power supply can then power our heater or solenoid or whatever we happen to have in series with it. So you can see there's clearly two circuits flowing, only one is controlled by the other. So the next thing we want to discuss is the power needs and limitations. So matching the energy requirement in both circuits. The questions we have are, can the RCX provide power needed to operate the relay? Can the second 12-volt power supply supply the energy necessary to operate the heater and the solenoids in our system? So we can compare these the model needs to the limitations of the hardware, and we'll take a look at that here. Alright, so in the model here, the RCX is represented by the power supply and the switch. Internally, the RCX programming opens and closes the switches and determines how much voltage and what the shape of that voltage waveform is. So as it's flowing here, we can see that some of the energy is consumed by the first resistor and the voltage divider, and so in this case it has 40 milliamps flowing through it, a 100 ohm resistor, and a 4-volt drop. If the relay needs 5 volts, as we hover over the relay coil, it has 5 volts coil voltage and 40 milliamps going through it. And so this part of the circuit consumes, if we add this up, the current and voltage from the power supply is providing 40 milliamps and 9 volts, which is approximately 360 milliwatts. And so as long as the RCX can handle providing 360 milliwatts in real terms, this will work out just fine. So we'll pause this and we'll take a look at the secondary side of the relay, so the side where the coil contacts are operating. Again, we've got a light bulb simulating our heater and solenoid on this circuit. As we close the switch, the 12 volt power supply is providing about a little over 400 milliamps at 12 volts. And so come around and look at the bulb. The power requirements on the bulb showing about 4 watts. Of course, we'll be powering multiple items with the same power supply, so we're going to have to check the measurements, add them up, and see if it's appropriate for the power supply that we have. You'll be actually checking the ratings on this power supply to see what it says on its label. These measurements will allow us to answer the questions. I'll pause this here, move it out of the way. So those measurements taken in class will allow us to answer these questions. Can the RCX provide power needed to operate the relay? Can the second power supply provide the energy needed to operate the heater and the solenoids? This allows us to understand the limitations of the hardware and their needs. So during week 1, we'll be dealing primarily with the primary side of the relay, the RCX outputs, and taking some current voltage measurements from that. And then during week 2, we'll be creating the voltage dividers and doing power measurements on the loads on the secondary side. So good luck in week 8 and 9.